We're now at a point in our technology where simulating a car's aerodynamics accurately is a real possibility. When we test cars in wind tunnels, the accuracy we can get is around 1% and in some cases even more. And historically, CFD hasn't been able to deliver results even close to that. And worse still, it hasn't been able to deliver results that are accurate enough for us to not have to use wind tunnels. But technology-wise, we are now getting pretty close to being able to do that. So while the technology is there, we now need to figure out the simulation method that will give us the most accurate results. Like, there are literally hundreds of different settings you can pick from for a simulation, and that results in millions of different combinations you can use. So finding the right combinations is tricky. And to give you an idea, choosing the right turbulence model, for example, so the set of mathematical equations that predict how much turbulence there is, can dramatically affect where separation occurs on a car. If you have a car with a delicate window, for example, with a rear window, then one turbulence model might say that separation occurs over it, and hence you get a lot more drag. But then another turbulence model might say that the flow stays attached, and you get a lot less drag. So these options, and many more, are super important, and that's what we're looking at today. Which options give the more accurate results? And to do that, we're looking at this paper called Turbulence Modeling Effects on the CFD Predictions of Flow over a Detailed Full-Scale Sedan Vehicle. It is open access, so you can find the link below. And when I first saw this paper, I thought that it was actually to do with NASCAR because I saw that it was from North Carolina here, and NASCAR has a center there. But then I saw that it is actually from Hyundai, and they did it in conjunction with UNC, which also has some NASCAR stuff as well. So currently, when it comes to simulating cars, two general approaches are using RANS and DES. So RANS is typically the less accurate of the two CFD approaches, but the major benefit of it is that it is way quicker. So DES is generally more accurate, but it takes a lot longer, like 5, 10, even 20 times as long. And for those of you who don't know what DES is, it stands for Detached Eddy Simulation, DES, which is a hybrid of RANS and then something called LES, which is much more accurate. And how it works is that near the surface of your object in CFD, you use RANS equations. Then as you go farther away from the wall, LES equations start to kick in. And the reason why it uses RANS in the naval region is that if you were to use LES, you'd need a lot of cells because you need to pick up all the different turbulent structures, at least the turbulent structures that are important, the ones that are being created and destroyed. On the other hand, RANS uses something called turbulence models, which really simplifies the turbulence generation and destruction process. So you can use far fewer cells and still get somewhat similar results, but the downside is that it's probably not going to be as accurate. It's going to be somewhat in the ballpark, but not as accurate as DES or LES. So DES then combines these two approaches where you have RANS and LES to try to get a good trade-off happening. So DES is kind of like a half step up in accuracy. It's not the full step up to LES, but it's definitely much better than RANS, theoretically speaking. So DES is even more complicated than that because you can now divide it up into some categories. So the original version is DES, but what early users found from this version was that it triggered LES too soon in the simulation. So that led to inaccurate results, and particularly in the automotive industry, the aerodynamics there. As a result, DES was improved to create something called DDES, which stands for Delayed Detached Eddy Simulation. And what that means is that the LES part of the DES simulation kicks in farther from the wall, farther away. That's all well and good, except even this new method was still causing LES to kick in a little too soon. So again, the DDES method was refined more, and a new method called IDDES was made, and that stands for Improved Delayed Detached Eddy Simulation. So the researchers who named this were optimistic that it was improved, and in this podcast we'll be looking at whether it was or not, at least for cars. Now, because DES uses RANS, turbulence models are also really important for it too. And let's cover what the turbulence models are, and well, at least what they considered here, and how they differ. So they list a bunch of ones that they considered here for the RANS only simulations, and that was the realizable K-epsilon model. There's something called the, Abe Kondo Nagano K-epsilon model. Then they also had the V2F model, also known as V squared F K-epsilon. Then they had the SST K-omega model, which is my personal favorite. Let's just quickly go through what each one of these means and how they differ. So the first one is called the realizable K-epsilon model. Now, I've always found it to be a weird name, but anyway, in a nutshell, it was developed to be an improvement over the traditional K-epsilon turbulence model by altering the eddy viscosity term and also basing how the turbulence dissipation how it dissipates on the mean squared vorticity fluctuations. So honestly, in most aerodynamics, the realizable K-epsilon model isn't that good and sometimes worse than the traditional K-epsilon model, but we have to see how it performs here. Now for the Abe Kondo Nagano K-epsilon turbulence model down here, the authors say that it uses the Kolmogorov velocity scale instead of the friction velocity. What does that mean? Well, in a nutshell, it means that this turbulence model is using how turbulence in the form of the smallest vortices break down. Now, this turbulence model isn't that widely used, and in fact, many CFD softwares don't even include it. So if you were to be using your CFD software, you may not be able to find it. So it'll be interesting to see how that performs here. The next is called the V2F, which I actually haven't used, at least seriously, for anything. So I've just played around with it a little bit, but here it'll be interesting to see how it performs compared to the other ones. Now, it's based on the K-epsilon family, which are the turbulence kinetic energy and the dissipation of that turbulence kinetic energy respectively. But there are two more variables that they can consider. It's a 4-equation model. They use the velocity scale and something called the elliptic relaxation factor. Now from equation 14 here, that's the velocity scale, which really refers to just a normalized velocity. Then finally we have good old faithful SST K-omega, which usually performs very well, particularly with IDDES. Now, it is effectively just a combination of the K-epsilon and K-omega turbulence models, so you hopefully get the best of both worlds, and we'll see later on how it performs in comparison to the other ones too. Now, that is for the RAN simulations. What about for the DDES simulation, so DDES and IDDES? Well, the authors go on to explain some shortcomings of the various DDES approaches, and one of them having DES, which remember is prone to switching from RANs to LES a little prematurely, is too close to the wall. So effectively, that produces something called grid-induced separation, GIS. What happens is that because LES gets triggered close to the boundary layer, or inside the boundary layer even, so the flow really close to the wall, there is artificial flow separation now occurring, which really shouldn't be occurring. So in a nutshell, these authors wanted to see how DDES and IDDES fared. So those are the simulation methods they are looking at in this research. But what about the car they used? Well, because this research is partly from Hyundai, it's no surprise that they used a 2014 Hyundai Veloster here, as you can see in figure 1. It's a little hatchback, so it's, I guess, not a sedan technically, but it's close enough, I guess. So the front ground clearance was 143 millimeters. And they say that they removed the small objects around it, such as like the nuts and bolts, and even they closed some of the small holes and gaps around the car. And overall, I think that this shouldn't make too much of a difference, largely because the flow is mostly turbulent over the car anyway, so these small items won't really trip the boundary layer because the boundary layer is already turbulent. So getting rid of them is okay from that point of view. Another thing is that these small features are kind of variable anyway. I mean, there are literally tolerances for manufacturing cars, and no car will be exactly the same as another car. One car might have a gap somewhere of 1 millimeter, another car might have it as 2 millimeters. So trying to get some car representative of all these cars is kind of not really possible. It doesn't make sense from that point of view. There's always tolerancing in manufacturing. So I think that this car is pretty decent overall. Now, this is the car they tested, and they did it in 2 different configurations. The first is the regular car here. Then the second one, which we can see in figure 2, this is the radiator, like the grille slicing through. We see, and figure 3 as well. So we see that in figure 2, the radiator for case 2 is now angled down a little bit. And they also, in figure 3, there are some blue bits showing the grille is being closed a little bit. The reason why the authors considered this configuration as well, this case 2, was that they apparently have found that this reduced the cooling drag, which kind of makes sense in terms of at least closing the grille. That usually does reduce cooling drag a little bit. So let's move on to their general CFD setup, because this is really important now as well, because you need to have everything really in the CFD lining up well in order to get accurate results. You can't just have one thing and not the other. So in figure 4, we see their general CFD setup, and this is their general domain. It's pretty decent. I'm not sure exactly why they picked these dimensions. I can't seem to find the reason in the paper. But based on them, I think that this is probably about the size of their wind tunnel test section. And if it is, then this is a really good idea by the researchers, because one major problem that many people who are doing simulations have is that they might simulate the exact same object as they test in the wind tunnel, but they have a different domain, and that could change the results. So for example, let's take the side walls. So that here we see that they're 10 car lengths away from wall to wall, and well, there's going to be a boundary layer building up on them as the flow goes along. That then results in a negative pressure gradient forming through the test section, and that could encourage flow acceleration or flow attachment, or any number of flow separation, or any other number of phenomena. So if you don't test the exact same setup as you have in your wind tunnel, then you can have a different effect, and that could be the difference between your CFD matching your experiments and it not. So as I said, they did a really good job here. I think that it's their wind tunnel test section here. I suspect it is, but I'm not 100% sure. Anyway, they used Star CCM Plus, which is a really great CFD software, but it is quite expensive. And on that note, if you want to learn how to do your own CFD, but don't want to spend the thousands and thousands of dollars per year on licenses for the top softwares like Star, then check out our OpenFOAM course and link below, because OpenFOAM is just as powerful, and in some cases even more powerful, as these other top CFD softwares, but it's completely free. The only downside is that it's really hard to learn. So that's why we have the courses in the link below. So check them out. Anyway, the speed was 70 miles per hour, so 31.293 meters per second, they say. Exactly. Just as a side note, calculating that it is 31.293 meters per second is probably not that accurate, because their wind tunnel test data probably has a different air density to the standard one of 1.2 kilos per cubic meter. Now, anyway, something I really appreciate with the simulation is that they even modeled the rotation of the cooling fan inside of the radiator section. They use an MRF approach, which is pretty standard for it. I mean, there are some inaccuracies with it, but it's pretty minimal, so it's pretty decent. Now, they also used the MRFs for the wheels, and they say that they made the volumes between the spokes in the rims MRFs to pick up the pumping effect properly. So for those of you who don't know what the pumping effect is, that is when the spoke rotates around, then pushes the air, and that creates more internal drag. It's an effect that isn't talked about too much, but is definitely real and should be considered. So I really like that the authors understood that and implemented this method to pick it up. Now, for their mesh, they used 75 million cells, and they cover later in their study, a mesh-independent study, where they jacked the cells up to 100 million for the RANS RKE model, and they found that the drag coefficient changed by less than 1%. They then also looked into a finer mesh for the IDDES model, which resulted in 87 million cells, and the results are in table 1. So let's go down to there quickly. Here we go. So as you can see, there is almost no change, 10.9% compared to 10.8%. So I think it's safe to say that the 75 million cells are used is enough, and the grid is independent now, so that's quite good. Now in figure 5, we can see the mesh around the car, and you can see that there are several refinement regions. You can see where it goes from very coarse to very fine. What that means is you don't just have a couple different size cells in the domain, but you have, as you can see here, these 5 different ones. And that is good because while it might be tempting to go from a really coarse mesh to a really fine mesh in one jump, that can produce errors because in the fine mesh, you're picking up all these really small scale stuff, especially with the DES approaches. But with all of a sudden going to the coarse mesh, you have all this stuff being lost. So by having this gradation, you get more accurate results. Now in figure 6, we see the Y+, and for pretty much the entire car, it's below 5, which is really good. So up to here, their safety is pretty much as good as you can get. There are some minor things you can improve upon, but it's very good so far. Now they talk about the hardware they use for the simulations, and I'm really amazed at this researcher's determination because they used only 96 cores for all these simulations. And now if you are only doing a couple simulations, then that's fine, but they did a bunch of simulations, and the RANS ones took 28 hours, they say here, to do just one, and the DES ones took 250 hours to do just one. So that's 10 days. CFD always highlights the will of the human spirit. Now, we come to something a little annoying, actually. So in the drag and lift force section, so here, they say that due to the proprietary nature of the data, the drag coefficient values presented in the paper were normalized using an arbitrary reference value, such that the baseline car drag coefficient obtained from the RKE model matches the one the available data in the public. Now I don't get this. What they're saying is literally they've just normalized the RKE value to match what they just say the Hyundai gives. So I don't get that, especially because when they say in table 1, we see the percentage. They say that differences between the various simulations methods here and the drag coefficient, and they say that the RKE model agreed very well with the experimental data. So yeah, of course it did, because you said that you made the baseline artificially match the RKE model. It's kind of like saying the best looking human in the world is what I look like, and then showing a photo of me and saying, wow, that's the best looking human ever. That's because that's what I said the reference value was. So even if it's true, which it is, I'm not going to lie to you that it's true. The method you used to conclude that is fallible. So it doesn't make sense here. So looking at table 1, if you didn't pick up on that erroneous method to begin with, just above, you'd conclude that the RAND's RKE model is by far the best model because it is only 1% different to the experiments. Then everything else is like 10% different in the drag coefficient. Now, there are two things to note here. The first is that strangely, every other method is very different to the RKE. So shouldn't that raise some eyebrows that the RKE is really the only outlier here in terms of the drag? Everything else is like 10% different. The second is that even if you don't have any experience with CFD in cars, but just with CFD itself, you should be pretty shocked to see that one of the worst TMS models, and with the least accurate method, i.e. RANS, is accurate more than anything else really tested. So while the authors are using the RKE model as a golden child, I'm actually going to say that the DDES and IDDES ones are almost certainly better from theory and from practice and experience. And we should be using those as the standard going forward to look at this paper. So from here on in, we can see how these differences in simulation methods affect the results with respect to the DES approaches. I think that should be the benchmark, not the RKE model. Now, moving on to this one to table 2, we see how the various force coefficients change between cases 1 and 2. And as the author said, yep, we do get a massive reduction in the cooling drag between case 1 and case 2. So you can see here, case 1 and case 2, CD drops. On average, it's like 25 counts for the RANS cases. That's really surprising and it's really big. In fact, bigger than I expected, because usually that's about how much the cooling drag in a car is anyway, 25 counts. So this is kind of suggesting that angling the radiator a little and closing off some of the grill effectively eliminates the cooling drag, or at least most of it. I find that a little hard to believe. And in fact, if we look at the DES results, there is only a few counts difference, so like 3 counts and 0 counts, which to me is much more reasonable. So that, I think, is a strong indication that the DES simulations are doing better than the RANS ones. As for the lift coefficient in table 3, we see the deltas, so the differences between the two cases, case 1 and case 2. And there is actually a very large change between the two cases with all these different CFD approaches. The only problem is that between the various CFD methods, the values change from minus 28 counts here for IDDES to plus 65 counts. So what that is showing is just how variable the lift coefficient is depending on the CFD approach you take. Now, what are some reasons why we get such large changes in the drag and lift coefficients with these different approaches? Well, figure 10, we can see the accumulated drag coefficient over the vehicle. So I like these graphs, they're pretty cool. What this means is that as you go from the front to the rear of the car, we can see how the drag coefficient accumulates. And something real quick is that if you look over the roof, so this portion here, we see that all the CFD simulations show a drop in the drag coefficient. Now, I'm not exactly sure why for this particular car that's happening, because we don't have the pressure on the windshield given, but I suspect that there is a higher pressure over the middle of the roof than on the windshield near the roof, so middle compared to the top of the windshield. As such, the pressure difference results in some negative drag. That's what I think is going on here. That's why we get this drop. It's effectively thrust occurring here. So anyway, looking at these lines, it's clear that the RKE line, which is the light blue one, is much lower over the hood than the other simulations, all of them really. And this is a major source of the lower drag coefficient that it gave in the tables above. Why do we get the lower drag here? Again, we don't have the pressure over the hood, so it's hard to tell, but I would be inclined to say that the RKE TMS model doesn't model the boundary layer over the hood correctly. And that is actually a thing that could lead to one major problem of the RKE model, which is a tendency to inaccurately predict separation 2. So I think that is what is happening here. Now, looking at figure 11 down here, we see the differences, the deltas, in the accumulated drag coefficient between case 1 and case 2. And the majority of the changes occur between the grille and the front windshield. Now, we also see here more information suggesting just how much worse the RKE CFD is. You can pretty much see that all the other simulations show very similar trends, but the light blue line here, which is for the RKE model, has very different trends. So again, the RKE RANS model should theoretically be one of the worst, and it is consistently giving very different results to all the other models, including the DES ones. So I think it's safe to say, and conclude here, that it's the worst one, and not the best at the very least. As a side note, it is very impressive that the other RANS Turbulence models, including the AKN, the V2F, and the SST ones, give very similar trends to the DES ones as well. So given that they take like 1 day to run instead of 10 days, in some situations, it would make much more sense to use them instead of DES, save a bit of time, get pretty accurate results, but you're still ahead overall. So they're quite impressive. Now in figure 13, we see wakes behind the car, and some streamlines showing some vortices. So the RKE model, which is the top left one here, gives very different results that there is this huge vortex off the rear window. The DES models show a vortex too, but they are much smaller. So in this plane, the RKE is more similar to the DES ones than the other 3 RANS ones. Now in figure 14, we see the changes in the pressure. Let's zoom in a little bit here. Too much, there we go. Now these are in reference to the RKE model, so a delta. And this is for the pressure coefficient. So if you don't know what that means, check out our video on YouTube called Aero Fundamentals number 12, Pressure Coefficients Explained, or Pressure Coefficient Explained, sorry. And that will explain to you what these really are and the deltas. So if you hadn't seen the differences in the wake from figure 13, you'd be really surprised that the top 3 cars, which all are RANs, have far greater changes compared to the RKE model, which is also RANs, compared to the DES ones, which are the lower row here. But after seeing figure 13, it's not so surprising. And this also shows just how much of a difference the wake shape has on the car's rear pressure coefficient, on the rear of the car. As a side note, if you want to get a high pressure coefficient on the rear, that will result in a lower drag. So you really want to jack that up as much as possible. A lower pressure coefficient usually results in much lower drag. So what this figure 14 is showing is that the other RANS models, the top row, have lower pressure coefficients compared to the RKE model. And that means that more drag will probably be registering here, which is kind of what we saw. They had a 10% increase. As for the DS ones, we need to see later on why those are increasing as well. Now, just comparing the bottom row, so the 2 DES models together, the IDDES model, so the right one here, is predicting lower pressure around the rear wheel houses and also over the diffuser. So let's zoom in a little bit here. There we go. So around these regions, the rear wheel house and the diffuser. That's not great. That suggests more running perhaps needs to be occurring here. Anyway, let's jump to figures 17 and 18 because figure 16 is not that interesting. So figure 17 and 18 here, they show planes cutting through the car at various positions, and these positions are shown in figure 17. So the first one is just at the front of the front wheels, the second plane is just at the rear of the car, and the third one is just a little further back than that. Now, the planes show the velocity, where red is generally better and blue means awake, and from 0 to 32 meters per second. Now, these figures are interesting, but figure 19 is a little more interesting because it shows the differences, which make it a little easier to tell what's going on. So let's look at that. So I should note that these differences are referenced to the IDDES fine simulation, which in itself is fine, but I don't know why they're now using that as the standard and not the RKE. Up until now, everything they've been doing has been referenced to the RKE Turbulence model, and now it's to the IDDES fine simulation. Anyway, whatever. So in the first plane, which is right at the front wheels, this plane here, there is minimal difference across the simulation, so you can see it's all very similar. Let's zoom out a little bit. There we go. In the second plane, which is right at the back of the car, I would say that the V2F model, so this third row here, is giving the worst results because there are these massive velocity reductions over the top of the rear wheel houses. So right here. Then continuing downstream to the third column, and we see them as well here as well. And that's a little surprising that the RKE model, so the top right one here, is giving the best wake out of the RANS models, really, compared to the DS one. And then the 2 DS models are giving almost identical wakes, really. There's almost nothing here, just tiny differences. So from all of this, I think we can definitely conclude that the DES simulations are the most accurate overall. From everything we've seen, the drag coefficients seem to be good for everything except the KE model. We've got coefficient, well, we can't really tell whether that is good or not because they're all over the place and we don't know what the experimental values were. So I think the DES simulation gave better wakes, but that can't be determined conclusively with the data they've given, but it's likely. So to simulate a car accurately, I think DES is the way to go from this paper, at least, and from real life experience. But there's a little more to the authors included here in this research. They also looked at how case 1 compared to case 2. So in figure 20, we see the change in the pressure coefficient between case 2 and case 1, where red means that the pressure coefficient is higher for case 2, where blue is lower. So immediately the RKE CFD is giving weird results because the entire car except the engine bay is blue. That just doesn't make sense, so let's just ignore that one. The rest of the simulations literally show the exact same thing, where the pressure coefficient in the engine bay is much higher for case 2, where the radiator is angled and the grille is a little blocked. Now the effect that it has on the wake can be seen in figure 21, and the results are a little strange. So in the RANs, the simulations show pretty much the exact opposite trends, where they show that let's zoom in a little bit here actually, comparing SST perhaps to the DES ones. Here we go. So for example, they show the top middle of the car's wake has a higher velocity, so red here, but the DES simulations show that it's lower, it's blue. Then over the rear wheel houses, there is a velocity deficit, so blue here. Then for the DES, there's a slight increase, red. So maybe the cooling flow is even more sensitive to the CFD model than the car in general. But to find that out, we'll need to look at that in another podcast. And with that, we come to the end of this one. If you liked it, make sure to hit the like and subscribe button. And if you want to learn CFD so you can do simulations like this or anything else you want to do, then take our course in the link below for OpenFlow. And we'll see you one. Peace, amigos.